In our previous video, we set up this situation where an ice cube at minus 15 degrees Celsius was warmed all the way into gaseous water. Let's follow through it this time and actually calculate it. So let's have a problem where we have a 12-gram ice cube at minus 15 degrees Celsius, and we want to take it all the way to 120 degrees Celsius gaseous water. Our goal is to find the energy at each step, as well as the total energy. Well, because we have to do this in parts, we're going to need a couple calculations. First off, we're going to have one that is a solid going to a solid. However, this will be minus 15 degrees up to 0 degrees. We're then going to have 0 degrees solid going to 0 degree liquid. This will be our melting step. We're then going to have 0 degree liquid warm up to 100 degree liquid. This will be where our water starts to get warm until eventually it starts to boil. After that, our 100 degree liquid is going to turn into 100 degree gas. And finally, we're going to warm up our gas. Our 100 degrees Celsius gas is going to turn into 120 degrees Celsius gas. So I have 5 parts that I need to calculate. Well, if you are within a phase, that is where we used our heat capacity. We need Q equals ms delta T. If you are transferring between phases, then we have our Q equals m delta H. Our first step here is in phase, solid to solid. So this is going to be a Q equals ms delta T. The energy of this is going to be the mass, 12 grams of ice. The S value, which for solid water is 2.05 joules per gram per degree. And our change in temp, well, remember that our delta T is always equal to temp final minus temp initial. And so 0 minus negative 15, that is a positive 15 increase. Our delta T is 15 degrees. Whether that was Kelvin or Celsius is irrelevant because it's still a 15 degree increase. Despite that our S value had Celsius in it, if it had Kelvin in it, I still would have used 15 because going from 258 Kelvin to 273 Kelvin is still a 15 degree Kelvin change. Well, we can calculate out the energy for this one step. 12 grams times 2.05 times 15. 369 joules of energy to heat that ice cube up. So it was in a really good freezer, well below 0. We take it out and we start warming it up to 0. It took 370-ish joules of energy to accomplish. Next, we have to go through a phase change. We're going from a solid to a liquid. This is a Q equals m delta H of fusion as we are melting. We have to put energy in to make it become the more energetic form. So we use the positive version here. If we'd been freezing this, we would have been taking out this much energy. We would have had a negative 6.02. But as we were warming this up, we're going to add this much enthalpy. And so our energy required to melt this ice cube, well, we've got 12 grams. And it is, let's put this into joules, 6,020 joules per mole. Oh, wait, that's a problem. We're not in moles. We're in grams. So we're going to have to do a little calculation there. Hey, 12 grams, it's 18.016 grams in 1 mole for our water molecules, which means that was never really 12 grams. That was 0.67 mole. 0.67 mole times 6020, that is 4,033 joules to melt. Significantly more. 15 degree change for the solid, was less than 1/10 of just getting it to turn liquid at the same temperature. Phase changes are energetic. Do remember to watch your units. We need moles for this one. It's possible we could adjust our fusion into per gram, but often we will find our fusion values in our texts as per mole. So if you need to convert it, do watch for that. Next bit, we're going from our liquid to our liquid. So we're back to Q equals ms delta T. Well, my mass is 12 grams. That didn't change when it became a liquid. S value for liquid water is 4.184 joules per gram per degree Kelvin or degrees Celsius. And our delta T, well, we're going to end up at 100 and we start at 0. So temp final is 100 minus 0. That's going to be a positive 100 degrees Celsius increase. 12 times 100 times 4.184. This comes out at 5,020 joules. So heating liquid water a full 100 degrees takes almost the same amount of energy as just getting it to melt. Another example of the very high energy of a phase change. This is also part of why it takes so long for lakes to freeze over in the winter. Getting that liquid, even if it gets cold, to actually turn solid requires a great deal of energy to be removed from the lake. Continuing down the line, we have another phase change. We're on our boiling step. So this will be a Q equals M delta H of vaporization. Well, we found our moles before, because our delta H vaporization is actually in moles instead of mass. And so instead of mass there, we'll need to adapt it into the moles. 0.67 mole for our 12 grams of water, and 40,700 joules per mole. This comes out at 27,270 joules. Well, that's more than everything else combined so far. Boiling off water is actually extremely difficult to do. It has a very high energy of vaporization. Water has very good attractive forces. It holds itself together quite nicely. Taking our ice cube and bringing it all the way up to boil took about a third of the energy of actually boiling it. Our last bit then, we're going to heat up that gas 20 degrees. I'm just going to do that one in white. I think the rainbow will be a little hard to read here. Well, we're gas to gas, so we're back to Q equals ms delta T. 12 grams, S value for gaseous water, 2.08 joules per gram per degree. And we're going up from 100 up to 120. So 120 minus 100, it's a positive 20 increase. 12 times 20 times 2.08. Approximately 500 joules. So we can see from the different steps which are the most difficult to do, what the relative amount of energy is required for them are. Vaporization is the most difficult, pulling all of the molecules apart. You have to overcome every intermolecular force. It takes a great deal of energy. Just getting things bouncing a little faster from heating them up doesn't take anywhere near as much. In the end, our total energy for this ice cube to go from minus 15 all the way up to vaporized gas comes out at 37,191 joules. Of which, just for quick reference, the water phase going to gas was 73.3% of the energy. But here we can see heat capacity and its interactions. When we want to calculate something going through a phase change, we can see the phase change calculations and how they work together to find the total energy needed to take a material from one state at one temperature to another state at a second temperature.